All right, so we're going to take a look at decimals with square roots and the Pythagorean theorem.
Are these the?
These are the last two sections of chapter 5.
So we should be
was it
taking
5, yeah, 5, 7, 5, 8, right? Yeah, 5, 7, 5, 8. So think about something like 3 to the second power. Right? Thank you. We also call that 3 squared because if you take 3 times 3, multiplication can always be interpreted as an area. In this case, I would have a square that is 3 by 3, right? So that's why we call it 3 squared, because geometrically, it's literally the area of that square right there. And again, if something is 3 by 3, then that means I can break it down into smaller 1 by 1 squares, and there's going to be 9 of them.
What is area equal? Is that length times width?
Yeah, so in this case,
by...
I'm looking at area as base times height. So I have a base of 3 there, and I have a height of 3 there.
Is it divided by?
Well, that would be triangles. So this is just for squares and rectangles.
Okay.
So, and again, this is the fundamental idea of area in our society. We measure area in square units. So things like this right here. So square feet, square centimeters, square miles.
So it's base times height divided by?
It's just base times height, that's it.
Well, for triangles, it's
base times height divided by 2.
Okay.
Yeah, because you can look at a triangle as half of a rectangle or a parallelogram.
And the perimeter, what is that?
We'll look at perimeter later.
Okay.
Yeah, for now, we're just going to focus on area because I want to get into the idea of a square root. So a square, 9 is the square of 3. Because I took 3 times 3 and I got 9.
So the square of 100 is 10?
100 is the square of 10. Right, so if I take 10 and I raise it to the second power, that means take 10 times 10, which is 100. So we could say 100 is the square of 10. Because we literally have, when I'm thinking about it this way, a square that measures 10 units by 10 units. Right, so that's kind of, I don't know if I can quite fit that on my screen here, but if that's 3, 10's probably way up there and way over there. So I have this big, and there would be 100 of squares that size inside if this were 10 by 10. So we can say 100 is the square of 10. Going the other way, we can say 10 is the square root of 100 because that is the number we squared to get 100. All right, so I'm going to write that down. So 100 is the square of 10. Reversing that, 10 is the square root of 100.
Okay, so the square root of 100 is 10.
Correct.
Okay.
And there's a shorthand for writing that. Just like I can write 3 squared equals 9, reversing that with symbols would look like this. 10 is the square root is that symbol right there. It looks kind of like a division box, but it's got this little hook out front of 100. And calculators have that button on.
So if there's a number inside that little square root box, we're looking for the square root of that number?
Correct. Yeah, so what could you multiply it by itself to get that number? Okay. So for example, if I wrote this, we're asking ourselves, what number would we square to get 36?
So you'd have
Is
to
the
divide.
question that's asking. Right now, I shouldn't have wrote those equal. Let's do that again. So let's do this. That equals what? Means what could you square to get 36? What times itself is 36?
3, no.
8.
8 times 8 is 64. 6. 6 times 6 is 36. Correct. So since 6 times 6 is 36, that means the square root of 36 is 6. Now, similarly, it was mentioned 8. If I take 8 and square it, that means 8 times 8, or 64. So reversing that, the square root of 64 has to be 8. I got a couple things to go over, and then I'll take questions, okay? Unless you have a question as to what I have right here.
I'm gonna ask for a pencil.
Ah, pencil. Yes, here you go.
Thank you.
You can keep that. Now, here's the deal, though. Not every number has a perfect square root. So if I asked for the square root of 60, what does that equal? That means we're trying to find a number, a question mark, that we could multiply by itself to get 60.
30.
Well, hold on. We know that 8 times 8 gives us 64. So that means it's got to be a little smaller than 8.
But 7 doesn't work.
7 times 7. Yeah, so here's the catch, right? So I know that 7 squared is 49, and I know that 8 squared is 64. So the number I'm looking for is somewhere in between 7 and 8. And it turns out it's going to be a decimal. It is very hard to calculate by hand. So we use a calculator. So I'm going to go whip out my calculator. If you haven't got one out yet, please get out a calculator. I'm going to use my Desmos calculator. And there is a square root button on most scientific calculators these days. And so I click that first. And then I say, I want the square root of 60. And the calculator says it's 7.749, blah, 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 blah. It goes on for a ways. How far? Turns out it goes on forever. And it doesn't repeat a pattern. Fractions repeat patterns. Square roots often do not. So the best I can do is approximate it. So in this case, I might be told to approximate this to the nearest hundredth. So then I would say, okay, I want to keep that much. The 5 here says round that 4 up to a 5. So I would say this is about 7.75. So the square root of 60 is approximately 7.75.
Are we gonna have any of those on the test?
No, because the test we're going to have is going to not involve calculators, so we won't have to worry about it. But this is something you need to know for other math classes in the future.
Right.
For sure, this is going to come up a lot. Just to double check that, if I take the number above here, remember a lot of calculators have a previous answer button. So if I say take that previous answer and raise it to the second power, it should say, oh yeah, that number squared is 60. Okay. But if I round at any point, it's not going to be quite there. Like earlier, I called it 7.75. And if I square 7.75, it'll be almost 60. Here it's a little over because I rounded up. If I instead kept more decimal places, like let's say I typed 5 decimal places. So that would be 7.745. 9, and then rounding that 6 up would be a 7. And if I square that, it's going to be closer than it was before. So we can always get closer. But the bottom line is to undo a square, we use a square root. And we almost always have to use a calculator to evaluate that. All right, next. This is useful in geometry because of a thing called the Pythagorean theorem. And the Pythagorean theorem is related to triangles that have a right angle, and a right angle is a square angle for 90 degrees. So I have to have what's called a right angle, which you could also call a square angle.
Is there a difference between right and left angles?
So why did we end up calling this a right angle? Historically, I don't remember, but there isn't a left angle. And it's not a right or left idea. The
Okay.
right part just means square or 90 degrees.
Okay,
So it's not using it in the same thing as right versus left. And a right triangle based on the right angle has legs. So this is a leg on this side, and this is another leg on that side. And the side opposite the right angle is always called the hypotenuse. And what humans discovered like 3,000 years ago, which is kind of wild, that if you, let's say this leg is 3 centimeters long and this leg is 4 centimeters long. What humans discovered thousands of years ago is that if you build a square off of each leg, so this would be a 3 by 3 square, and you build one off of that leg there, so that would be a 4 by 4 square. 3 squared plus 4 squared, if we add those areas together, so that would be 9 and 16, which is 25, match the area of the square that comes off the hypotenuse. Sorry, my square's a little janky there. So this square has to have an area of 25. If its area is 25, what do the measurements of its sides have to be? What is there a number that we can multiply by itself and get 25?
5 times 5.
Yeah, 5 times 5. So in other words, I want to know what is the square root of this sum of squares. And it turns out in this case, it's a nice number, but it's usually not. And we'll do some other ones in a minute. So this is what's called the Pythagorean theorem.
Is there any division in that?
No. It's just squaring, adding, and square roots. And we'll do a couple more examples of this.
When it's in a problem in a book, it doesn't have all those extra squares. It will just have numbers.
Yeah, I'm drawing the squares just to demonstrate what it means,
Visual.
but usually we won't need to do that.
But to represent the square, it's going to be squared
Yes,
in the problem.
there's
Okay.
always going to be squares in the Pythagorean theorem. Yeah. And this is what humans discovered around 3,000 years ago. And it's a pretty remarkable thing that we still use a lot today.
And the hypotenuse is,
Hypotenuse is always the long side, the side opposite the right angle.
and it's
The
gonna,
right angle is always going to be the biggest angle. So the hypotenuse is always going to be the longest side.
and that one's always going to be a square root.
Any of them can be square roots.
Oh,
it
they're all
turns
square
out.
roots. Oh,
Yeah,
okay.
so because anytime we square, 3 squared is 9, we can go backwards and say 3 is the square root of 9. So square and square root relationships go back and forth all the time. Yeah. So in general, here's the Pythagorean theorem. If we have a right triangle, then we have legs. The legs are usually labeled A and B. The long side, the hypotenuse, is usually labeled with a C. And what we humans discovered a long time ago is if you take the lengths of those legs, so A is that length, could be 3, could be 5, could be anything, and we square it, and we take the other leg and measure it, and then we square that measurement, that's always going to be equal to the square of the long side. Hey, Preston. And this relationship of the lengths of each of these sides is what's called the Pythagorean theorem, this equation right there. So next, we'll draw a couple of triangles. Given two sides, we can always figure out the third side with this relationship. So let's try a triangle where the base of the triangle is 5 and the height of the triangle is 4. And usually base, well, always base and height have to be perpendicular. That means right angle. I want to know what is the length of that long side. So I'm going to call that missing side C. And the Pythagorean theorem says if you take the legs and measure them, so I have a 5 and then square it, and then I take the 4 and I square it, that's always going to be equal to the square of the other side. Now, I don't know it, so I'm just going to call it C squared. 5 squared is 25. 4 squared is 16. 25 and 16 is 6 and 5 is 11. Carry 1, 2, 3, 4, 41. So I'm looking for a number that I can square to get 41. Well, 7 squared is 49. 6 squared is 36. So it's somewhere between 6 and 7. So if it's not a number we recognize as a perfect square, then we have to say we need to ask our calculator what is the square root of that number. So we have no choice but to go over to our calculator and ask. So choose the square root button on your calculator, then type the number you want the square root of. And so this says it's about 6.4. I'm just going to go to 1 decimal place. Even if I went to 2 decimal places, it's still 6.4. So that missing side is about 6.4. So does that seem reasonable? Well, if my sketch is good, graph paper would have helped. So I was saying this side was 5. So 1, 2, ooh, not very good measuring sticks there. Let's try that again. Oh, wrong button. 1, 2, 3, 4, 5. That's about 4. Does it seem reasonable that this side right there should be about 6.4? And yeah, that seems reasonable. It's the longest side. It's definitely smaller than 10 and bigger than 5, just looking at it. So 6.4 seems reasonable for that length. All right, let's try another one. Let's try a triangle where I have a base of 5. And this time I'm going to go for a diagonal of 6. And I want to know what is the height. And this may not be drawn to scale. I'm just going to make a little disclaimer there. I don't have a measuring stick out at the moment. All right, so what does the Pythagorean theorem say about this? Well, we have a leg. Let's say 5 is leg A. We're missing leg B, and we have the hypotenuse C. And the Pythagorean theorem says a squared plus b squared, the legs squared, equals the hypotenuse squared. And so plugging in what I have, well, I have an a squared, so that's going to be a 5 squared. I don't have b, so I'm just going to leave it as b. I do have c, so I can say that's a 6 squared. 5 squared is what?
25.
25. 6 squared?
30.
Nice. And b is still unknown.
So don't you have to subtract 25 from
Yeah, so we know how to solve equations, so we can solve this. So I'm going to have to subtract 25 to the other side. And that's going to leave, that goes away, right, a 0. On this side, 36 minus 25 is 11. get a little more room there.
What's the
So
square of
now
11?
I have b squared is 11, which means b has to be the square root of 11. What number can I multiply by itself to get 11? Well, 3 times 3 is 9, so it's bigger than 3. So I'm going to ask the calculator, since it's not a perfect square that I recognize. .32 if I go to 2 decimal places. Oops. So wavy equals means I rounded. It's not an exact answer, but it's close. Now that seems reasonable. The other triangle I had 5 by 4 and the diagonal was 6.4. This diagonal is a little smaller, so the height should be a little smaller. So that seems reasonable.
So did we just do the two-step equation right there?
This is a two-step equation, yes, because one step was to do the subtraction and the second step was to do the square root.
Okay, so where I think I'm getting confused is adding that extra step that I normally just do in my head.
Yeah, and square roots we can't easily do in our heads.
Well, see the 25 where you subtract it there?
Yep.
Normally I just take the 25 and subtract it from 36.
Yep.
I mean, I think that's the way I was taught in element, like
Yep.
middle
Yeah, so
school.
that's one step doing, so this part right here is one step. The step is subtracting 25 from both sides. Then we clean it up, and then we have one more step to do to get an answer. In this case, the step was a square root. In other situations, it was a division. Okay, so it just depends. Right, and that's the essence of sections 7 and 8 in chapter 5.
I had a question. So on the test, we did a division